It's 1918, California, San Francisco Bay. The bay is a world-class natural harbor, maybe the best in the world. A gift from God, some would say, and entirely due to your own efforts, of course. It has a thriving marine industry on its shores. Lumber, oil, agriculture, railroads, all on a large scale. By 1900 alone, it handled 6 million tons of international goods. San Francisco's vitality was put to the test and proven on an extraordinary scale when the city was almost completely destroyed by an earthquake in 1906, and then built back, greater than its previous glory, in time for the Panama Pacific International Exposition in 1915. The Bay Area is looking up. Nice harbor you got there. It would be a shame if something happened to it. What if some pest, some little worm, hove into view one day and, in the course of a single year, destroyed $500 million in infrastructure in modern dollars? What if piers and wharves and bridges suddenly started collapsing into the water? What if it left you and your investors scrambling to figure out what the hell just happened, how to keep your marine industry alive while you figure it out, and what to do about it for the future? Is your industry up to the challenge? This is the story of an invasive organism, an introduced organism, or perhaps a cryptogenic one that isn't clearly either native or introduced. It's about a shipworm, Teredo nivalis, and the havoc it caused early in the 20th century, in and upstream of San Francisco Bay, and the national concern and response to it. You probably haven't heard about it because it's pretty much a solved problem by now. It's still a serious challenge, but there are accepted answers to what to do about it. But it's useful to study the response and to know this history because something like it can and will happen again. Before we get going, remember to like, subscribe, and check out the Tor store. Get yourself a Jollibee mousepad or this fantastic t-shirt featuring all the curiosities. Put some stickers all over your laptop, your locker, the back of the stop sign near your house, whatever. Link in the description to the store. I'm your host, Tor Parsons. If you don't buy anything from the store, you will be hunted down by my co-hosts, Jollibee the Durian, Thimble the Doll, and Slud the Shoggoth. And welcome to Tor's Cabinet of Curiosities. This topic was suggested to me and the script co-authored by my friend and business manager Jim Hickstein. It comes from a book he has. Jim collects books, mostly nonfiction. The Bell Labs episode we did together came partly from books he had. Jim's library is nothing if not eclectic. It does not contain books on every imaginable subject, like a public library, but it does contain books on subjects you would never imagine. This episode of Tor's Cabinet of Curiosities is based in part on this book, Marine Borers, stick with me here, and their relation to marine construction on the Pacific Coast being the final report of the San Francisco Bay Marine Piling Committee Hill and Kofoid editors published by the committee, San Francisco, California, 1927. Jim says it's one of his prized possessions. A lot of technical books in the 19th and early 20th centuries had rather florid titles like that. I bet there's a light novel out there with a similar title. Also, Jim thanks his friend, who's also named Jim, one Jim Warhol, and yes, he is related to Andy, for giving him this book. I can almost guarantee you have never heard of this committee or the crisis that precipitated its work, but boy was it a crisis. The book turns out to conceal a story that's way more interesting than I thought at first. Truly you cannot judge a book by its cover. So put on your 1927 hat and let us explore. A shipworm eats wood. Ships were made of wood for most of history. Iron ships started to come in during the 19th century. Isambard Kingdom Brunel's Great Britain of 1843 was the first ship built entirely out of wrought iron, and steel became a thing for ships in the 1880s. Around 1849, remember, this is California, most of them were still wood and still under sail, and the piers and wharves and things that they use in harbors were, and still often are, made of wood. A wooden pile is just a tree trunk, stripped of its branches and usually its bark, turned upside down and shoved into the earth in order to support something. Wooden piles are ubiquitous in construction, on land and sea, right down to the present day. Does the wood in a pile need any special protection in water? Well, that depends. Is the water salty, brackish, or fresh? Wood rots faster in salt water, less because of properties of the salt water itself and more because of what lives in salt water. Shipworms have been known since ancient times. The native range of our little nemesis Teredo nivalis is unknown, but it likes warmish salt water such as that in the Mediterranean and the coasts of Europe. It wasn't noted in the Northwest Atlantic, the US East Coast, until about 1839. It was definitely introduced to the west coast of North America, from San Diego to southern British Columbia. Ships brought it with them. What is a shipworm and how does it burrow into wood? Well, a shipworm is actually a clam. It is still also a worm. You may be aware of the fun fact that there is no real zoological definition for a fish. Every binding definition for a fish you could find includes some things that are definitely not fish. You just have to know it when you see it. Same is true of worms. In fact, worms are an absolutely vast category. You know what a phylum is, right? The second biggest level of classification of organisms under the kingdoms. Phyla are really broad categories. The animal kingdom comprises just 31 phyla. All animals are in one of 31 phyla. Vertebrates are a single phylum, and there are 14 phyla that are just worms. 14. The animal kingdom is almost half worms. And since there's no real definition of a worm, you can count other long, thin, slimy things as worms that don't belong to those 14 phyla, like shipworms, which are really weird clams. In the Pacific Northwest where I'm from, we've got these huge clams called geoducks, which look like what they look like. That's a big-ass siphon. Most clams have siphons, a tube they can extend when they're buried in sand or mud to breathe through the water above. A handful of species have siphons so big they can't retract them into their shell, like geoducks. But if you extend the siphon size to shell size ratio to the point where the shell almost disappears, that's a shipworm. A clam that is also a worm with a tiny little shell that can't be used as a shell. But the shell of a shipworm isn't vestigial, it's not useless. The shell is how a shipworm burrows into wood. It uses the two parts of the shell hinged together, the ridges of the inner shell as a saw to bore into the wood, and the outer part as a rasp, enlarging the burrow as it goes along, excreting a material that forms the wall of the burrow. Incidentally, this kind of digging, and in fact Teredo nivalis specifically, here's a better picture of one, inspired Sir Mark Brunel, Isambard's father and also a legendary Victorian-era engineer, to devise his tunneling shield. This enabled him to complete in 1843 the first tunnel under a navigable river, the Thames, which is still in active service today as part of the London Overground commuter rail system. The front of the shield supports the roof of the tunnel while workmen remove material from the face. The part of the lining excreted by the shipworm is played by other men building in brick behind, because, alas, nobody has yet built a tunneling shield that poops. Several methods of protecting wooden piles from attack by worms and other things have been around for quite a while, anecdotally if not scientifically studied, chiefly saturating the outer part with coal tar creosote. But it was thought that rivers, carrying fresh water to the sea, would keep the water's salinity low enough in the estuaries and the northern part of the bay that one could use untreated wooden piles and get away with it. Because money, of course.
Money!
And it worked, right up until it didn't. So what do you do in such a crisis? Form a committee, of course. A year before the discovery of gold in California and 3 years before statehood, San Francisco had a population of about 800 souls. In 1849, the gold rush brought a sudden influx, and since the Transcontinental Railroad was still a dream, they all came by sea, in wooden ships. These were promptly deserted by their crews, who went off in quest of gold, until later that year there were, quote, between 300 and 400 square-rigged vessels lying in the bay, unable to leave on account of want of hands. Most of them never left. Some hulks were turned into wharves and buildings. A few made municipal facilities. The Euphemia became a prison, the Panama a church, and the Apollo a saloon. The core of San Francisco, around the Embarcadero and Ferry Building, is still home to buried ships that had a second lease on life as the city was built around them. Bankia was probably the first of several types of shipworm in the bay, which joins Teredo in the family Pteridinidae. With Limnoria, another shipworm present in the South Bay at the time, writers would have noticed the damage the worms did early on, as this worm does its work out in the open at the surface of a pile, making it thinner until it snaps. But Pteridinidae do their work inside the pile without visibly affecting the outer surface. Bankia showed up around 1850, Limnoria about 1870, and Teredo, the granddaddy of them all, was first recorded at Mare Island in the North Bay in 1913. The wharves in San Francisco were developed chaotically, in common with most developing ports. The city filled in parts of the bay to make new land, and sold it to pay for the whole thing, but the fill just slid into the water. They needed to build a seawall, but that would be hugely expensive. A financial crisis in 1854 didn't help. In 1863, a state board of harbor commissioners was created to remedy the chaos. It is recorded that on the day of their first meeting, the Stewart Street Wharf collapsed, dropping 150,000 feet of lumber into the bay, and the Vallejo and Jackson Street wharves failed shortly afterward. How was your day at the office, dear? In 1869, as many viewers of this channel will know, the Central Pacific Union Pacific final link in the Transcontinental Railroad was completed, and in consequence, the bottom dropped out of trade by sea in San Francisco. 426,000 tons coming in by ship in 1867 became 176,000 in 1869. Difficult as this may be to believe, the main way trade got from the East Coast to the West Coast before the railroad was on ships that went around the southern tip of South America. Obviously, nobody would do that if there were any alternative. Most of the development and wharves moved over to Oakland, where of course the railroad terminated, as railroads then and now don't naturally float. Now the railroads got involved in a big way. The Central Pacific extended its Oakland pier to 11,000 feet long. This became the Long Wharf. They had a dock in Oakland that at its maximum length extended practically halfway across the bay to San Francisco. Only reason they didn't build a bridge the whole way was so that the South Bay would stay navigable. The dock was low above the surface of the water, not high enough for ships to fit under it like today's Bay Bridge. And they had to constantly be replacing the piles driven into the mud, one by one. The piles were naked wood, not coated in creosote. Central Pacific's chief engineer, S.S. Montague, thought and wrote in 1873 that the piles along the Oakland waterfront would be undoubtedly immune to attacks from Teredo because of the fresh water coming in from the Carquinez Strait and flowing along the shore. Well, he was almost right. He was right for a while. The Bethel pressure cylinder creosoting process, injecting tar into a pile under pressure, had been brought over from England in 1838 and proved its value, but the creosote leached out. Bethel, an Englishman with the very American idea that if a little is good, more is better, was saying to amp it up, use 10 times as much. It took them 50 years, but this was eventually done. In 1889, the Southern Pacific Railroad was doing it in a temporary plant at San Pedro in the Los Angeles area. A number of other treatments and coatings and wraps were tried: asphalt, limestone, canvas, burlap, ship felt, to varying successes. Surface treatments were eroded by storms and other abrasion, and even the properly creosoted piles succumbed to dogging and pike pulls, you'll learn soon what those are, and cutting and framing after treatment. And they still only got 10 years out of a protected pile. At the Golden Gate, unprotected piles lasted only a couple of months. So they despaired of such things prematurely and went all in on mechanical methods of protection, notably concrete. Even the concrete piers failed, but this turned out to be caused by not getting the concrete far enough down in the mud. It wasn't inherently bad, and neither was creosote. 1917 was a year of low rainfall, and the salt water of the bay moved far upstream. This was made worse by the rice farmers clear up above Antioch, taking so much water out of the river for irrigation that the landowners downstream sued to protect their river rights. Plus ça change. There was even a proposal to halt the upward march of salt water by putting a sort of dam across the bottom of San Pablo Bay and turning it and Suisun Bay and the Carquinez Strait into a freshwater lake, except in wartime, where they would lower the thing to let ships have free passage. This idea did not have legs even in 1927. Imagine what the frogs and the fish, not to mention activists, had there been any, would have made of that. For more on the environmental movement later in the century, watch my episode about the Cuyahoga River catching fire. Mare Island, location of a Navy base since 1854, was attacked by Teredo in 1917, but not badly. Limnoria was in the lower bay, but low salinity kept it out of the upper region, and Teredo's hidden work meant the alarm was not raised. Not yet. Rainfall recovered a bit in 1918, but this only set the stage for the massive destruction of 1919, which was a 40-year low for rainfall. In the fall of 1919, wharves began to collapse, and this continued into the next year. Ship impacts, which normally make the piles bend, would now break them clean off. Vibration, other impact loads, and sometimes just their own dead weight were enough to do the trick. 50 structures went down, costing some $15 million at the time. By the time the committee was formed, the destruction continuing until most of the untreated piles were consumed, it was $25 million. That's over $460 million in 2025, pushing $500 million. The committee had their work cut out for them. Early in the year 1914, the activity of shipworms was noticed in the dikes of the Mare Island Navy Yard at the upper extremity of San Pablo Bay, which is the northern arm of San Francisco Bay, and two other points on the east shore of the bay. Note that by dikes we mean sea barriers. The other kind of dikes are in Berkeley. Some attacks had been seen there since 1870, but records were spotty and damage was not serious. For many years before 1914, San Pablo Bay, Suisun Bay, the Carquinez Strait, and the lower course of the Sacramento River had attracted plenty of large industries. They all built structures in the water, on untreated pilings, because they hadn't reported any shipworms in the area yet, and the experts of the time believed that the combined flow of the two major rivers flowing into the bay, the Sacramento and the San Joaquin, would keep out the salt water, and hence the shipworms. The 1914 attack appeared to be sporadic, like those before, but in 1917, shipworms, now identified as Teredo, appeared again at Mare Island and spread rapidly and got much worse. In late 1919, parts of many waterfront structures, and in some cases whole docks, began to fail. By 1920, it was a critical local situation. The Bay Area needed to find a way to deal with the worms fast, or else its days as a global port were going bye-bye, and California's fortunes would fall with the Bay. On June 16, 1920, it was brought to the attention of officials at the American Wood Preservers Association. They appointed a special committee on July 22nd and instructed them to report to the association's 17th annual meeting in San Francisco the following January. But they couldn't wait for January. The committee set to work in late July 1920 and grew as new local interests were enlisted. At almost the same time, the Forest Products Laboratory of the U.S. Forest Service, henceforth the FPL, the people who brought you plywood, among much else, were proposing to study the marine piling problem over the entire coastal waters of the U.S. The FPL's work, starting in 1910-1911, also involved the Forest Service's California District and the University of California system through Professor Charles A. Kofoid for the biological aspects of the problem. They ran some experiments in San Francisco and San Diego of different kinds of trees, methods and materials of protection, but those were scattered and more or less fragmentary. FPL now decided to bring it all together. The committee started with about 20 members and grew to more than 50, with representatives of the various funding organizations and technical or other contributors, quote, selected for specific personal attainments or other reasons deemed of value to the committee. Real transparent. The officers came from the Southern Pacific Company, a railroad, henceforth just SP, McCormick Lumber, California and Hawaiian Sugar Refining, C&H, and the FPL. Other members of the executive committee were from UC Berkeley, Shell Oil, Standard Oil, Associated Oil, and the Board of State Harbor Commissioners. The general members are a who's who of any outfit with anything in the water at the time. More lumber, oil, and railroads, the U.S. Navy from as far away as Bremerton, Washington, civil engineers, contracting engineers, a consulting timber engineer, and even the San Francisco Bridge Company. They set to work. First was to survey the damage over the past 3 years, find out where the borers are and were, their growth and habits, and to learn as much as possible about other factors influencing their attacks. Then about methods and materials for protection, their effectiveness, and their cost. It was organized in 3 phases: hydrographic, biological, and engineering. They sent out a questionnaire to all the affected shoreline industries, which provided valuable information and helped plan the work of the many field investigations, especially experiments in the biological phase. They arranged to pull up existing piles or watch them be pulled in the normal course, and just to rifle through the files of all the affected organizations. The work throughout 1920 was duly reported at the meeting on January 26, 1921. It pointed out the scope of the work yet to be done and the need for, you probably saw this coming, continued authority and more money. They couldn't possibly finish in under 3 years, they said. They got a lot of their overhead gratis, so all the money went into productive work. A lot of result for the money, even compared to other efforts at the time, but they still needed to hire 2 full-time people, a biologist and a chemist, and they asked for another $30,000, over $500,000 today. And they got it. They split into 9 subcommittees, as committees do, but at this remove it does seem reasonable, given the scale of the disaster, and that nobody knew how to fight it. It was a multi-front war, humanity's best and brightest against the combined forces of millions of worms. The committee set up a biological field lab and experiment station at, and kind of under, the Southern Pacific's freight pier next to the Oakland Mole. That was the long wharf that stretched almost halfway across the bay. A mole means a pier that water can't flow under. CNH provided another field lab at their sugar factory in Crockett by the Carquinez Strait, where the Teredo's survival was at a critical tension point. And UC Berkeley's labs were used extensively. There were 5 test stations for exposing various treated samples of wood to attack, and 8 salinity stations where the water was sampled. As all that was going on, the National Research Council, an outfit that had been created by the government a decade ago to coordinate scientific research during World War I, got in on the act. They formed their own special committee on marine piling investigation to build connections with other countries working on this problem. The president of the University of California appointed those members from the UC faculty. It involved work in San Francisco, Los Angeles, San Diego, and 11 Pacific Ocean stations outside the US. The upshot is all the detailed data and tabulations and technical recommendations and specifications for marine pilings, the bulk of the final report. Don't worry, it's too detailed and technical for a video like this. I promised I wouldn't make a pun involving the word boring. Building anything in seawater is especially challenging. The superstructure has all the problems of building on land, and the substructure has to stand in mud and resist tidal currents, waves, storms, ships, other floating menaces, weathering the chemical action of seawater, and for timber, the ravages of shipworms. It's expensive to build and maintain things in water, and deterioration costs both money and disruption when things need repair. Customers want their needs met at the lowest first cost, which, for marine construction, usually means untreated timber piles. Just because similar structures nearby have not been attacked does not let you off the hook. Borers are all along seacoasts and can survive in low salinities, as low as 5 parts in 1,000. Rivers and estuaries won't necessarily save you. Salinity varies, and structures can be destroyed in a few months. Teredo nivalis breeds in July and August, and has been known to destroy unprotected piling by October. Engineers in this situation need to know a lot about these borers and the methods of protecting against their attacks in advance. Research was needed. The engineer has to create structures with the greatest economy, so there is a constant search for better practices and a ton of experimentation and testing. This is a big part of what the committee carried out. It's also vital to know what has gone before. Ideas are constantly appearing under new names involving old schemes long found worthless. See also J.D. Clark's 1972 book, Ignition, An Informal History of Liquid Rocket Propellants. Not obviously relevant? Well, he wrote a whole book as a rant about his younger colleagues wasting a lot of time and money through not knowing the history of their own field. Rocket fuel consists of the same thing independently invented again and again. This committee had to make sure that the same wouldn't be true of protecting piles from shipworm. There are 4 main categories of places where bad things happen to marine structures. They are air-water interface, water, and mud. You may notice that's all the places a marine structure can possibly be in. All 4 sections need to be treated differently and guarded against different threats. The air-water interface is where most weathering happens, where Limnoria shipworms attack it, and where the various metals tried as protection tend to corrode, as well as, for example, reinforcing steel in concrete. The water section is where the Teredo shipworms do their work, so air-water is hardest on concrete, the water section most critical for timber. The water level also goes up and down, sometimes quite a lot. San Francisco Bay is not the Bay of Fundy. The tidal range is about 5 to 8 feet, with wharf floors built about 15 feet above low water. At Sacramento, the river has an annual range of as much as 31 feet, and wharves are built higher, 36 feet above low water. All that partly wet structure is subject to attack. Currents are also serious, especially along the San Francisco waterfront and at the Golden Gate. The bay is 50 miles long, and the Golden Gate is less than a mile wide and 300 feet deep. The tidal flow there is over 2 million acre-feet. This may be why no escape from Alcatraz has ever been successful, although it's possible that one once was, which is another story. Because of the serious currents, successive government rulings established two lines along the San Francisco waterfront: the bulkhead line, beyond which you can't build solid masses like seawalls, and the pier head line, beyond which you can't put anything permanent at all. In between those two lines, if you want to build a pier or something, and you do, it can't have the currents pushing up against it, or it'll be worn away. This is why they still use pilings there today, to let the water go past. In San Francisco, the original 1851 bulkhead line had a sawtooth shape, just where the streets ended, with piers sticking out at odd angles through not having been specified. The eddying currents caused sediment to build up around wharf slips and needed constant dredging. They tried filling in the waterfront again in 1878 and ended up with the smooth curve we have today. The current is much happier with that. Shipworm attacks are greater on the side of a pile facing the current, and in deeper, saltier, and warmer water, other things being equal. But Bankia cetacea likes cooler northern waters. Salinity might range from almost nothing fresh water to ocean water of 30 to 35 parts of salt in 1,000 of water. And the shipworms care about this. The danger point is about 15 parts in 1,000, this or higher, and shipworms, if present, will go to town. Teredo likes 10 to 20 parts, Limnoria and Bankia 20 or higher. Infestations can move by driftwood or log booms or water currents that carry the larvae. Apparently unaffected structures in one area, built of unprotected timber, often led to others being built the same way on the unwarranted assumption that something about them makes them immune to shipworms. Purity of the water also figures in. Structures near sewer and industrial outlets, remember this is 1919, were somewhat protected. Shipworms like clean water. Fortunately, it was the 20th century in a port city in America. There wasn't a lot of clean water to go around. These were still the days when a river catching fire was kinda normal. Treating a pile with creosote, which only penetrates some distance in from the outside, not all the way through, is not the end of your work. It's easy to damage the protection by poor handling. Limnoria especially will take advantage of the smallest openings that go into the interior unprotected wood. Apart from the Southern Pacific Railroad's creosoting plant for their own use, there were no local plants for doing this, so the finished products had to travel long distances and be stored locally, all contributing to damage. They were sometimes made up into rafts and dogged. Metal rods with loops, eyes, were driven into the wood, and these were tied together with ropes. That had to stop. The use of dogs should be unconditionally prohibited, said the committee. Axes, pike poles, peavies, and boat hooks all took a toll. The dogs, as a wise man once said, were out. It was also important to remove breeding grounds. An infestation will continue as long as there's exposed, unprotected wood available, and after being attacked, there were a lot of derelict structures just left to collapse and float away. The bay was so thoroughly seeded up that every floating fragment of wood was likely to be infested to its capacity. One pile may harbor 150,000 shipworms, each capable of producing 2 million larvae to attack other piles. Douglas fir was the most common species of tree used for timber piles. They were plentiful in Northern California and the Pacific Northwest, hence cheap, available up to 100 feet long, or 125 at the Southern Pacific's Dumbarton Bridge, though they weren't easy to saturate with creosote. The committee threw everything at the problem to see what would stick. A huge number of other kinds of tree were studied, from as far afield as Africa, Australia, the Philippines, and South America. Redwood, western red cedar, and Port Orford cedar, quote, have been and still frequently are asserted to be immune to borers. They are not. A redwood pipe carrying water to the bay at 135 degrees for some reason was not only attacked by Teredo, but they followed the pipe 1,000 feet up onto land and destroyed the redwood tank at the end of it. Remember, the worms like warm water. Other trees didn't show a big improvement on Douglas fir or just weren't available in the quantities needed, since even protected piles had a limited lifetime. They tried nailing sheets of metal on the outside, iron, zinc, copper. They all corroded or were expensive, or both. They left the bark on the trees. They tried paint and any number of supposed patented processes called Paraffin, Moran, Colombia, Argentine, the Key West armor system. Seems that all those patented processes were grifts. One gambit involved making up a pile by nailing boards together so as to maximize the number of cracks, on the commonly accepted belief that a shipworm would not cross a crack. Limnoria, at least, didn't get the memo. Limnoria shipworms love cracks. The report mentions electrolysis, releasing chlorine, which would work if the water didn't carry it off. You can guess how that turned out. They even talked about, and maybe even tried, dynamite. It would kill things, to be sure, but the limited range and need for constant repetition were a problem. They finally concluded that nothing beat coal tar creosote and Douglas fir. It still had to be replaced a lot. It still got eaten by the worms, sometimes, but it was the least bad option, and today, it's still the least bad option. So the committee set about to document all their testing, chemical investigations, study of service records, and to write technical specifications for docks. This is kind of a sad conclusion. They didn't find some whiz-bang solution after all their experimentation. The real way to defeat the shipworms was the friend they made along the way. But that's how these things go. The committee still did research and made a conclusion. That's the scientific method. It doesn't guarantee a breakthrough. Sometimes the best solution you've got is to stick with the status quo, but you're only going to find that out by trying all the other solutions first. And the committee clearly felt triumphant about their work. What did they accomplish? According to the final report, a lot. It gave industry specifications and practices that they could use to avoid a repeat of the disaster, and it gave engineers what they sorely lacked before, namely, a way to determine much more precisely when and to what extent they needed to apply protection against shipworms and how much to expect it to cost. Holding the book in your hands, it's easy to forget the ignorance that preceded it and the cost of that. Spare a thought for $500 million. I don't know if this could have happened today. The number of cats you'd need to herd to get a focused, well-funded alliance of public and private interests together to solve a problem, even if it's one that directly affects all of them, seems insurmountable. I'm struck by the number of casual references in this book to putting infill in the bay, extending the waterfronts of San Francisco and Oakland. This was done again and again in the late 19th and early 20th centuries, easily, constantly, by city governments and port authorities. Large parts of both cities used to be bay not too long ago. When they had problems building infill, they were engineering problems, not political problems, and thousands of people in the Bay Area still live on infill today, which has survived multiple major earthquakes, so clearly the engineering struggles with dumping rocks and dirt in the shallow bay were never that difficult. Well, right now the Bay Area is suffering from what's arguably the world's worst housing shortage. It sure would be nice to have some of that infill today, right? We've physically expanded the size of San Francisco many times before, back in the days of the horse and buggy. Why can't we do that again? To my knowledge, no California politician has even suggested this as a solution because everyone knows building neighborhoods on infill in the San Francisco Bay in the year of our Lord 2025 is not something you can do anymore. Environmental groups would sue, even though the bay is cleaner now than it's been since the gold rush days, and building some infill where previous infill has been wouldn't destroy any pristine habitats. Owners of waterfront property would probably sue even harder because their property would no longer be on the waterfront. That would be a hit of millions of dollars to their net worth, and the government can't abide that. If you want to build tall buildings on the infill, even people living far away would be able to sue to block construction because it would affect their view. You can do that to stop distant construction that isn't affecting you at all, and people do, all the time. And because of all of these things, no large-scale infill project has happened in a major American city for decades, so there aren't any construction companies in this country that know how to build infill anymore, and the amount of red tape and political pressure that would surround hiring a foreign construction company would make that nearly impossible too. But maybe we can't do things like this because we think we can't. As I've said in my last few episodes, I live in New York now. The Pacific Northwest is my home, and I'll be back there someday for good, but I love the variety of people I can meet in this city. Last weekend I talked to a man who works for a committee kind of like the one that saved California from the worms. The committee in question includes heads of transit agencies, real estate firms, and transit policy experts from NYU, which is what the guy I talked to does. They'd been convened by the state of New York after the Trump administration canceled federal funds for an expansion of Penn Station, $16.7 billion that would be spent bulldozing an entire city block of Midtown Manhattan adding 8 new tracks to the 21-track underground station. Penn Station is operating at capacity right now. It's in need of an expansion, or, since the funds for building an expansion have been canceled, some other improvement. But what? Here's what that committee found. Penn Station is the end of the line for 2 commuter rail systems. New Jersey Transit trains exit the station to the west, going onto the Hudson River and fanning out across New Jersey. Long Island Railroad trains exit the station to the east, going under the East River and fanning out across Long Island. When one of those trains arrives at Penn Station, they have to wait, get a new crew on board, go around to the cab at the other end of the train, and leave back the way they came. Why do they have to turn around like this? Because they can't go onto the tracks run by another transit authority. Long Island Railroad trains can't go to New Jersey, and New Jersey Transit trains can't go to Long Island. But there's no infrastructure making that impossible. That's a political problem. The tracks out of Penn Station go both east and west. If you have a Long Island Railroad train come into Penn Station and then turn into a New Jersey Transit train, stopping there momentarily and then continuing along its way out to New Jersey, the amount of time and effort that would save is monumental. You don't need to build anything new, you just need to buy trains that can switch between the 2 different voltages the train's electrical systems use. And that's easy. There are already trains made in the USA that can do that. Just slap NJ Transit, Long Island Railroad, and Metro North logos on the same train, and you're ready to go. No need to build new tracks, no multi-billion-dollar expansion needed. Amtrak trains already do run through Penn Station, stopping there obviously, but most Amtrak trains that go through New York are traveling between Boston and Washington, D.C. New York is an intermediate stop. Currently, Amtrak trains spend 10 minutes stopped in Penn Station. That's a while, isn't it? Definitely longer than trains spend stopped at any other major station in any other global city comparable to New York. Just reduce the dwell time to 5 minutes, said this committee. Boom, now capacity is doubled. It's that easy. There is low-hanging fruit all around us for those with the eyes to see it. Just like the California Shipworm Committee found, the solution to improving Penn Station's capacity didn't require doing anything big. It's a little depressing how many problems that feel wickedly multifaceted and insurmountable just have obvious solutions that we don't go for simply because it feels too obvious, and obvious solutions aren't supposed to exist. But don't think of it that way. Think of how depressing it would be if there really were some law of the universe preventing us from solving big problems efficiently. America can still do big things if we are willing to look for solutions in the smallest of places.
Man in grey will get you now. You've got to hide or take